Welcome to our CathCAD software training series of videos. This video will provide information on the principles of mechanics of materials that is used within the CathCAD software. The material in this video will explain the critical inputs and outputs that are used and referred to in the CathCAD software. The material in this video will not teach you how to use the CathCAD software. We have other training videos that will teach the user on how to use the CathCAD software. Finally, we strongly encourage the user to take a basic class in the principles of mechanics of materials. This CathCAD training video will cover the following items. First, we will provide a basic introduction to the CathCAD software. Second, we will define the concepts of longitudinal, flexural, and torsional rigidities and how they apply to catheter design. Third, we will define the engineering material terms including modulus of elasticity, shear modulus, and Poisson's ratio. Fourth, we will define the specific material input variables used in the micromechanics model that forms a basis in the CathCAD software. Finally, we will define the area inertial equations used in the software. CathCAD is the software solution that allows the user to analyze and predict the mechanical characteristics of microcatheters. The computational algorithms are based on the following models and/or data sources. Mechanics of materials. Composite laminate theory. Tube buckling or kink radius computations are based on the model developed by Brazier in 1927. Vendor material data sheets are used for loading material properties for standard materials used in medical catheter products. These data sheets typically provide the material properties at standard conditions. The software computational engine is not based on empirical or tabulated measurement data. CathCAD is a predictive software model that allows the user to optimize material selection as well as the individual layer thicknesses to predict pushability, flexibility, torque transmission, deflection under a force or torque load, kink resistance including ovalization, strength of materials design analysis. This training video will provide the user of how the CathCAD software models catheter pushability, flexibility, and torque transmission. Hooke's law is an empirical law which states that the force, F, needed to extend or compress a spring by some distance, X, scales linearly with respect to that distance. That is, F equals sign Kx, where K is a constant factor characteristic of the spring, its stiffness, and X is small compared to the total possible deformation of the spring. The concept of Hooke's law is used to form the basis for the longitudinal, flexural, and torsional rigidity terms defined on the next 3 pages. Pushability is defined as the catheter response when an axial force is applied. For small deflections, the spring constant is defined as shown. K is a spring constant. E is defined as the modulus of elasticity. A is the cross-sectional area. L is the catheter length. We normalize this result with respect to catheter length by setting the catheter length exactly equal to the value of 1. We define the term longitudinal rigidity by setting it equal to the product of modulus of elasticity, E, times the effective cross-sectional area, A. Flexibility is defined as the catheter response when a force is applied perpendicular to the catheter longitudinal axis. For small deflections, the spring constant is defined per the equation as shown. K is defined as the spring constant, which is defined by the force divided by the deflection. E is defined as the modulus of elasticity. I is defined as the second area moment of inertia. L is defined as the catheter length. We normalize this result with respect to catheter length by setting the catheter length exactly equal to the value of 1. We define the term flexural rigidity by setting it equal to the product of modulus of elasticity, E, times the second area moment of inertia, Y. Torqueability is defined as the catheter response when a moment or torque is applied to the catheter as shown about the catheter longitudinal axis. For small deflections, the sprint constant is defined per the equation shown. K is defined as the torsional spring constant. G is defined as the shear modulus. J is defined as the polar moment of inertia. L is defined as the catheter length. We normalize this result with respect to catheter length by setting the catheter length exactly equal to the value of 1. We define the term torsional rigidity by setting it equal to the product of shear modulus, G, times the polar moment of inertia, J. The resulting catheter simulation model consists of analytical equations combined with the CathCAD software. The flexural rigidity, or beaning stiffness, applies to the catheter device tracking ability. The longitudinal rigidity term, or axial stiffness, applies to valve loading, sheath insertion, and/or valve deployment via a catheter device. Final torsional rigidity, or torsional stiffness, applies to the device alignment of the catheter device. We will now define the terms isotropic, orthotropic, and anisotropic for the viewer. An isotropic body has material properties that are in the same in every direction at a point in the body. An orthotropic body has material properties that are different in 3 mutually perpendicular directions at a point in the body. And an isotropic body has material properties that are different in all directions at a point in the body. For simplicity, the CathCAD software assumes that all materials exhibit isotropic behavior. In the CathCAD software, the individual layers are decomposed into 2 different material types. A layer may be a homogeneous isotropic material, or a layer may be a reinforcement layer consisting of A, isotropic matrix material, and B, isotropic fiber material. Micromechanics is the study of composite material behavior at the microscopic level. It is used to determine the modulus of elasticity and/or stiffness of the composite material in terms of the constituent materials. The underlying assumptions are provided on this page for the viewer to read and review. In general, the matrix material and reinforcing fibers are modeled as being homogeneous, exhibit linear elastic behavior, are perfect aligned and bonded, with no voids in the construction. All layers in the design are considered to be perfectly bonded to each other. If the actual constructed catheter design departs from any other of these governing principles, the CathCAD modeling results will depart from measurements made on the actual parts constructed. The next 5 pages define some of the modeling terms used to construct the longitudinal, flexural, and rigidity terms previously defined and used. Modulus of elasticity is a mechanical property of solid materials that measures the tensile or compressive stiffness when the force is applied lengthwise. It is the modulus of elasticity for tension or axial compression. It is defined as the ratio of the stress, force per unit area, applied to the object and the resulting axial strain, displacement, or deformation in the linear elastic region of the material. There are 4 different ways of estimating the modulus of elasticity from physical measurements of a device. These methods are illustrated on this page. The most 2 common methods are 1, the initial tangential modulus method, which is shown in the upper left-hand corner of the supplied figure, and 2, the secant modulus method, which is shown in the lower left-hand corner of the supplied figure. Poisson's ratio nu is a measure of the deformation, expansion, or contraction of a material in directions perpendicular to the specific direction of loading. Shear modulus, or modulus of rigidity, G, is a measure of the elastic shear stiffness of a material. It is defined as the ratio of shear stress to the shear strain. The shear modulus may be computed from the modulus of elasticity and Poisson's ratio, which were previously defined. The material input variables to the CathCAD software consist of the following 6 items. For fiber or reinforcement material, such as a stainless steel braid wire, the software requires the modulus of elasticity of the wire material, the Poisson's ratio of the wire material, and also the normalized fiber volume. For the matrix or polymer material, such as PBAX 72D, the software requires the modulus of the elasticity of the material and the Poisson's ratio of the material. The software also requires the normalized matrix volume. Given that we now understand the equations governing the materials in the CathCAD software, we now define the equations involving the area inertial properties of the catheter design. These equations are provided to the user for a single lumen catheter design. These terms are automatically computed in the software by the user entering and defining the catheter inner diameter, outer diameter, and the individual layer thicknesses. We provide a screenshot of the CathCAD user interface. The values of flexural, longitudinal, and torsional rigidity are provided as part of this output format. This completes this CathCAD training video. For more information, please visit our website at www.cathcad.com.